Alexa, tell the pump to turn on.
Turning pump on now.
Alexa, tell the pump to turn off.
Turning pump off now.
So the way this all works is
projects. Bad robot. Good robot. In addition to this,
send the meeting address to my Volvo. Start the heater in my Volvo. Prepare my Volvo.
When discussing ultrasound-guided peripheral nerve block technique, it is useful to describe basic nomenclature for needle and probe manipulation. Much of this is derived from the American Institute of Ultrasound in Medicine standards. We will describe the 2 basic scan planes, the 5 probe manipulation maneuvers, and the 2 needle approaches. In the following figures, we are looking at a schematic of an ultrasound transducer applied to a tissue-equivalent phantom, with 3 different embedded objects. A depiction of the ultrasound screen is inset. We generally image long cylindrical structures with an ultrasound beam that is essentially planar. Short-axis imaging cuts this cylinder transversely, revealing a circle. Long-axis imaging cuts the cylinder longitudinally to create 2 parallel lines. Long-axis imaging is of limited use in ultrasound-guided peripheral nerve blocks. An ultrasound transducer can be rotated or translated along any of its 3 axes. Hence, we need to use the AIUM standards so that we can communicate clearly with one another. Here we see an ultrasound probe moving and pivoting along each of its X, Y, and Z axes. Each of these movements has a name that we will define in the next section. Sliding is a maneuver that translates the transducer along the course of its structure, or perpendicular to it to scan adjacent structures. Compression is a useful maneuver that has numerous effects. First, it moves the active face toward deeper structures to make them appear more superficial. It also helps differentiate between different structures by their relative compressibility. Veins are easy to compress, arteries are somewhat compressible and pulsatile, and nerves are fairly incompressible. Rocking allows us to extend the plane of imaging when we are working in a narrow acoustic window. Rotation is used to switch between short-axis and long-axis imaging. Tilting allows us to scan along the course of a structure through a narrow acoustic window. In nerve imaging, it is critical to optimize transducer tilt to properly visualize nerve fascicles. Nerves are seen best when the scan plane is orthogonal to the course of the nerve. Given that we are most interested in nerves imaged on short axis, We will now look at how the needle will be seen as it approaches nerves. With the out-of-plane needle approach, the needle starts in front of the plane of imaging and advances until it crosses the plane of imaging as an echogenic dot. With the in-plane needle approach, the needle is visualized on its long axis as it advances within the scan plane. Now let's move on to show some of the common challenges with visualizing the block needle sonographically. Block needles are specular reflectors, meaning they reflect sound back to the receiver over a narrow angle. As the angle between the transducer and needle increases, less sound is reflected back to the receiver, and the signal becomes weaker. We can also see that this is true for sound reflected off the sides of the needle shaft. With the short axis out-of-plane approach, the needle will be seen best when the tip is within the plane of imaging. The shaft gives a signal that
ultrasound guidance for vascular access. We're going to be using a linear ultrasound probe to guide the positioning and placement of this needle to gain access to a vein, artery, or any other vascular structure that you need to get access to in a quick and fast, efficient means without jabbing your patient multiple times. Put your transducer on the patient's skin. Center the image, the vessel, in the center of the transducer face. We have multiple crystals across here. We're going to center the vessel directly under the transducer center so that when I enter the skin, I'm going to hold the transducer at an angle, I'm going to hold the needle at an angle, and hopefully they will meet at a point near the vessel in the center of the image. I'm going to keep advancing it until I see the needle show up in the image. I want to come in at a fairly low angle so that I can see the needle show up in the image above the top of the vessel. I don't want it to already be through the vessel. I don't want it to be below the vessel. I want it to see it on top of the vessel, because then I can position my needle right or left to put it directly over the top of the vessel itself. Once I'm directly over the top of the vessel, all I have to do is angle up and enter the vessel. By moving the transducer with the tip of the needle, I can follow it as it goes until I actually see it penetrate the vessel wall and enter and end up being center lumen on this vessel. And what I'm doing is entering the skin. I'm looking for my needle to show up in the image above the top of the, there it shows up. You can see it right there as I advance and back it up. That's the tip of the needle. And you can see I'm not exactly over the top of the vessel. So by angling the needle sideways, I can now advance the transducer, advance the needle. I can angle it over a little bit more and advance the transducer. Advance the needle, advance the transducer. Advance the needle and then the transducer until I'm right on top of it. Now that I'm right on top of it, I'm actually pressing on the vessel itself. All I have to do is bring the hub of the needle up a little bit, and I'm in. We're now in the vessel. At that point in time, I can now put the transducer down, can disconnect the syringe. You can do this without a syringe. You can look for your blood flash right here. I can thread my wire if I'm going to do a PICC line. If I'm going to be doing a venous ablation, I can get my guide wire in. Once the guide wire is in, pull the needle out, hold your guide wire, put in your introducer sheath right along the same pathway, and you've got instant access. So for vascular access, again, transducer, 90 degrees, vessels in a short axis, bevel up, enter at a very steep angle till you see the needle over the top of the vessel. Then all you got to do is once you get over the top of the vessel, angle up and follow that needle with the tip of the transducer. It's two-handed. You're advancing both needle and transducer at the same time, following the tip of that needle until it enters the vessel. Once it enters the vessel, you get your flash, put in your guide wire, and access is there.
The major limitation of Fourier transform is that although we access the knowledge about frequencies present in the signal, we lose all information about time. Fourier transform essentially squishes the signal in time to find the frequency components. The Fourier transform is a function only of frequency, but we don't know when certain frequencies begin and when they end. For example, think of the signal emitted by a traffic light. At first, it will be red for a while, which corresponds to an electromagnetic wave with a certain frequency in the visible spectrum. Then, for a few seconds, it will glow yellow, which has a slightly higher frequency, and finally, for some time, it will be green, which is a wave with even higher frequency. Obtaining a Fourier transform of this signal will give us three peaks, only telling which frequencies are present. We can indeed see that the signal is made up of three colors, red, yellow, and green. Now suppose the traffic light gets broken, and the order of colors gets all messed up. For example, it's yellow for 2 seconds, then green for 8 seconds, then again yellow for 1 second, and then red for 9 seconds. If you look at the Fourier transform, you will see pretty much the same picture with the same 3 peaks corresponding to color frequencies. Now suppose our traffic light malfunctions, and all 3 colors light up at the same time and persist to glow together, which would be a disaster for the road. However, the Fourier transform will continue to show the same 3 peaks, because the resulting wave is a sum of 3 colors. Frequency components are exactly the same as before, red, yellow, and green. This is why, hypothetically, if you receive hundreds of signals from traffic lights from all over the town,
Prepare walking.
I understand that you say prepare walking. Confirm yes or no.
Yes.
Roger. I'm doing it.
Walk forward.
I understand that you say walk forward. Confirm yes or no.
Yes.
Roger. I'm doing it.
Walk backward.
I understand that you say move backward. Confirm yes or no.
Yes.
Roger. I'm doing it.
Turn right.
I understand that you say turn right. Confirm yes or no.
Yes.
Roger. I'm doing it.
Stand up. Stand up.
I understand that you say stand up. Confirm yes or no.
Yes.
Roger. I'm doing it.
Detect object.
I understand that you say detect object. Confirm yes or no.
Yes.
What color is the object?
Red.
Detect read object. Confirm yes or no.
Yes.
I can approach the object by following the steps. Turn right 4.64 degrees, move forward 1.45 meters.
Click one.
The most common transducer types are dynamic and condenser. In a dynamic microphone, sound waves strike a thin plastic diaphragm and cause it to vibrate. A coil of wire attached to the back of the diaphragm vibrates along with it. As the coil moves back and forth, it passes through a magnetic field created by a magnet, which generates an electrical signal that corresponds to the sound. Dynamic microphones can handle even the loudest sounds without overloading, but this also means that they're not well suited to distant miking of quiet sources. Because the sound waves have to move the mass of the diaphragm and the voice coil, they usually have limited high-frequency detail, so they're better for vocals or horns than for stringed instruments. The size of the magnet makes it difficult to make a dynamic mic very small, which can limit your mounting options. In a condenser microphone, sound waves also strike a diaphragm and cause it to vibrate. The diaphragm is mounted just in front of an electrically charged plate. As the diaphragm moves back and forth, it changes the electric field between the diaphragm and plate, which generates an electrical signal that corresponds to the sound. Since there is no voice coil in a condenser mic, the sound waves only have to move the diaphragm. This gives condenser mics better high-frequency detail than dynamics. This makes them ideal for miking stringed instruments, percussion, piano, or subtle vocals. Condenser mics usually have higher output than dynamics, so they're good for distant or quiet sources. Since there's no magnet in a condenser mic, they can be made extremely small, which makes it easier to mount them in tight spots and make the mic less visible. Condenser microphones have internal circuitry that requires power to operate. Usually, phantom power is supplied through the microphone cable from the mixer or recorder.
With high sensitivity and excellent speaker recognition. The self-powered flexible acoustic sensor was fabricated by mimicking the operating mechanism of the basilar membrane in human cochlear. While low-frequency sound vibrates the membrane near the base region, high-frequency sound induces the resonance in the apex region. The resonances occur at different frequencies of voice depending on the width of the multi-channel sensor membrane, which enables highly sensitive acoustic sensor. In addition, the flexible acoustic sensor can acquire abundant voice information from the multi-channel structure. This multi-channel acoustic sensor covers the entire voice frequency range, providing much higher sensitivity compared to the reference microphone. Conventional microphones exhibit limited recognition distance due to low sensitivity. However, the highly sensitive flexible acoustic sensor could detect minute sound from a farther distance. The flexible acoustic sensor demonstrated machine learning-based speaker recognition, determining who is speaking and what is said. Using flexible acoustic sensor with simple algorithm, the error rate of speaker recognition is significantly improved, which allows personal-based artificial intelligence service such as TV, refrigerator, AI secretary, and smart home appliance. This flexible acoustic sensor can be applied in the intuitive voice user interface based on customized individual communication and biometric authentication.
Hello Indiegogo, we're Matrix Labs, an open source creation company consisting of a passionate team of 35, distributed around the world. We create versatile hardware and software which enable the convergence of IoT with artificial intelligence. We love creating and manufacturing revolutionary machine intelligent products, have shipped tens of thousands to over 50 countries, and have 2 successful crowdfunding campaigns under our belt. So what's next for us? Voice recognition. The only problem is that everything on the market is either too expensive, too complicated, or just not powerful enough. The best options are Amazon Echo and Google Home, but then you're locked into the respective services and integration. That's why we're proud to introduce Matrix Voice.
The cheapest, most developer-friendly, and most powerful development board for voice applications. Matrix Voice is for makers. It's for industrial and home Internet of Things engineers, from novice to hardcore developers. Matrix Voice is powerful. Measuring 3.14 inches in diameter, it offers a radial array of 7 MEMS microphones connected to a Xilinx Spartan 6 FPGA and 64 Mbit SD-RAM, which provides developers with the opportunity to integrate custom voice and other hardware-accelerated machine learning technology right onto the silicon. Matrix Voice also includes 18 RGBW LEDs, 64 GPIO pins for device-to-device connection, a standalone 2.4 GHz Wi-Fi and Bluetooth-enabled 32 bits microcontroller version of Matrix Voice is also an option, satisfying the demand for mass commercialization of voice solutions for industrial and home IoT. You start by plugging Matrix Voice into a Raspberry Pi or other single-board computers, or by connecting it to power for standalone use. From there, you can download our CLI tool and libraries to start programming. We have made the libraries in multiple layers, so you can directly program the FPGA, or use C++ via HOW, or go all the way up to MOS and program everything in JavaScript with only a few lines of code. On top of all of that, we include technology for far-field voice capture, beamforming, acoustic source localization, noise suppression, de-reverberation, acoustic echo cancellation, and voice recognition integration with Google Voice and Amazon Alexa. Plus, our Matrix OS has a suite of computer vision algorithms, including face detection and gesture recognition, so that you can integrate some of the most advanced computer vision algorithms in the world by simply attaching a camera to your Raspberry Pi. Matrix Voice came to life due to overwhelming demand from thousands of developers already part of our Matrix ecosystem. Comprised of our own OS, App Store, and our Matrix and Matrix Creator products. Matrix is our consumer-focused, sensor-packed IoT hub, winner of the CES Innovation Award, and successfully funded on Kickstarter, shipping Q2 of this year. Matrix Creator is our Maker Faire Blue Ribbon Award-winning sensor-packed development board for the Raspberry Pi, successfully funded on Indiegogo. We have shipped tens of thousands globally, and dubbed by Make Magazine as one of the most promising pieces of hardware.
Matrix Voice is for the do-it-yourself maker and enterprise developer. Everything is done. We just need to manufacture at scale so we can reach the affordable pricing of the board. Back us today, and together, let the world hear the voice of our creations. Thank you!
Hello, welcome you back to study MA4822.
Jasper. Lighting.
Which lights, your lordship?
Illuminate. And the lights come on. Jasper. Didn't hear me. Jasper. Lighting.
Which lights, your lordship?
Extinguish. Oh, well done, and the lights went out.